If you think about the progression of material in this course, we've started off talking about atoms, and then we built up to polyatomic ions and molecules, and we looked at their properties, and that's all great. Molecules are fantastic. But the thing about it is, most of what makes a substance interesting, most of what dictates its performance in the natural world, comes down not so much to the molecule itself, but oftentimes to the forces between molecules. And in this section, section 11.2, we're going to look at those forces, which we're going to collectively call intermolecular forces. This is easily the most important section of chapter 11, and I would argue it's one of the most important sections in the entire textbook. We're going to classify these intermolecular forces, or sometimes I'll call them IMFs, into 4 different types. And I'll go through the different types as we go along. You can see them here. I won't read them for you. All of these intermolecular forces are based on electrostatic attractions. That is the attraction between a positive charge and a negative charge. And as we discuss these, we're going to talk about where those charges come from, and then we're also going to look at how strong they are. It's important to differentiate intermolecular forces from true chemical bonds. So when we talk about molecular substances, as we see at the bottom of this table, nitrogen, hydrogen chloride, hydrogen fluoride. So we have covalent bonds within these molecules. They're all diatomic molecules. But then we have only intermolecular forces between molecules. And it is the intermolecular forces that are going to control things like the melting point and the boiling point. Right? For nitrogen to become a gas, you don't have to break apart the nitrogen molecule. You just have to overcome the forces of attraction between neighboring molecules. If we were to look at ionic compounds like lithium fluoride, right, where the attractions that are holding the atoms together are true ionic charges, electrostatic in nature as well, but much stronger. So we see that the melting points and the boiling points are at very high temperatures, over 1,000 degrees Kelvin. If we were to look at metals, here beryllium, but we could pick many different metals, we would oftentimes find that the melting and boiling points are also very high, right? And so this is telling us that the metallic bonds that hold the atoms together in beryllium or any metal are quite strong. And then if we look at a class of solids which are called network covalent solids, like diamond or silicon, in those structures there is a nearly infinite network of covalent bonds holding all of the atoms together. And you can see that the temperatures needed to overcome those bonds is incredibly high. Okay, so chemical bonds, very strong. Intermolecular forces, generally much weaker. So let's start our discussion with what is probably the simplest possible system. Let's look at the noble gases, helium through xenon. Now, I said just a minute ago that the intermolecular forces between atoms are electrostatic in nature. But if you think about a neon atom or a helium atom, what could be electrostatic about the attractions between these? They're neutral atoms. They don't form bonds. It doesn't seem like there should be a positive and a negative part to it. Yes, there's a nucleus and an electron cloud, but for 2 electron clouds to want to get close to each other, you would think that they would be repelled from one another. Yet, if we look at the characteristics of the noble gases, we'll see that if you cool them down enough, they all do become eventually liquids, and all of them except for helium will become a solid at sufficiently low temperatures. So this raises a couple of questions. What on earth is responsible for the atoms sticking together? And the second question is, why does this force of attraction, whatever it is, get stronger as we go down the group, as the atomic number increases, as the mass of the atom increases? Well, the answer to that is something called dispersion forces, or sometimes they're called London dispersion forces. Those mean the same thing. And let's take a look at what that is. Imagine that we have two helium atoms that happen to be right next to each other. Now, helium has a +2 nucleus and it has 2 electrons. And let's imagine these electrons are moving around, doing their wave-like dance, just minding their own business, right? But we also learned back in chapter 6 that, the probability of where the electrons might be at any given instant in time changes. So let's say at one given instant in atom B, the electrons both happen to end up on one side of the atom, on the left-hand side of the atom. Or we could think about them as waves, and we could say that the electron density at that given moment in time is higher on the left-hand side of the atom than the right-hand side of the atom. So that's going to make a dipole moment at that instant in time on the helium atom. And the dipole is going to be negative on the left-hand side and positive on the right-hand side. So atom A, which was just minding its own business until atom B went and did this dipole thing, it's going to respond to that. The electrons, being repelled from other electrons, are going to say, hey, I want to get away from this negative charge on my neighbor. And where did this come from? So they'll move over to the other side. And now we have a dipole moment on atom A. And then you can see that the partial negative charge on atom B and the partial positive charge on atom A are enough to give us an attraction between these two atoms. Okay, and we call that a dispersion force. It's important to note that the dipoles we see here are transient. They appear for a second and then they change and disappear. And if that happens on one atom, it's going to induce a dipole moment on its neighbors. The other thing to know about the dispersion forces is if you get into the physics of it, the strength of the dispersion force, it depends, yes, on the magnitude of the charges, but also on the distance. And it drops off as 1 over the distance to the 6th power. So what that means is that these forces are only relevant when the atoms are very close together. So if we think about something in the gas phase where the atoms are quite far apart and moving rapidly, the dispersion forces are really not important. It's only when we get into the condensed phases of matter, liquids and solids, that they become relevant. So what about the periodic trends? We just were looking at the noble gases, and so neon to argon to krypton to xenon. As we go down the group, the boiling point increases. And so that implies that the dispersion forces are getting stronger. And in the last lecture, when we looked at the halogens, fluorine, chlorine, bromine, and iodine, we saw the same trend, maybe even more pronounced. And we saw that something like iodine can have intermolecular forces that are so strong that it makes it a solid at room temperature. In both cases, because these are neutral, nonpolar molecules, the only intermolecular force is the dispersion force. So we can understand this periodic trend in the following way. If we look at a given atom, and how easily the electron cloud can be deformed in response to an electric field nearby, we would call that its polarizability. And what we see is that if you have a small atom with very few electrons, like helium, it's not that easy to polarize it because they're quite close to the nucleus and they're always feeling the charge of the nucleus. But on the other hand, if you have a large atom with a lot of electrons, like xenon or iodine, then the electron cloud turns out to be quite polarizable. From that, we can also infer that the dispersion forces are going to become stronger as the polarizability increases. And the polarizability is going to increase as the number of electrons increase. And of course, as the number of electrons increases, we would also see a concomitant increase in the mass of an atom or a molecule. So the net conclusion is that dispersion forces become stronger as the molar mass of a molecule or an atom increases. Put in simpler terms, we can say that heavier molecules are stickier. Of course, molar mass is not the only thing that matters. The shape of a molecule can also play a role. Here we're looking at two different isomers of pentane. N-pentane has a molecular formula of C5H12, and neopentane has exactly the same molecular formula. Therefore, they have exactly the same molar mass. The difference is, in N-pentane, the carbon atoms are all connected along a chain. Okay, so that makes this molecule have a cylindrical shape. Whereas in neopentane, you have a single carbon atom at the middle of the molecule, and then CH3 groups bonded in a tetrahedron to the central carbon. And that gives the molecule a spherical shape. And if we look at the boiling points, we see that N-pentane has a boiling point of 309 Kelvin, whereas neopentane has a boiling point of 283. So at room temperature, N-pentane is a liquid and neopentane is a gas. That implies that the dispersion forces in N-pentane are stronger than they are in neopentane. And we can understand that by thinking about the surface areas of these molecules. For a cylindrical molecule like N-pentane, there's quite a bit of surface area where the two molecules can approach each other and get close enough so that the dispersion forces are operative. Whereas in a spherical molecule, there's a smaller amount of surface area where the two can come very close to each other, so the dispersion forces turn on. So molecular shape also matters. Okay, now let's move on to the second category of intermolecular forces. These are called dipole-dipole interactions. These are present whenever we have polar molecules. Now, to understand them, let's go back to a Chapter 8 concept when we talked about polar bonds, dipole moments, and polar molecules. If we take a molecule like HBr, we know that the bromine is more electronegative than hydrogen, and so that pulls the electrons in the shared bond toward the bromine and away from the hydrogen. And that gives a partial positive charge on the hydrogen, a partial negative charge on the bromine. And so we can write a dipole moment that's shown here. Now, the dipole moment, which we calculated back in Chapter 8 for HBr, is 0.82 dBi. Many molecules are polar, like HBr, and have a dipole moment, not just diatomic molecules. Here's another one. This is acetonitrile, CH3CN. And because the nitrogen is much more electronegative than carbon or hydrogen, this molecule is also polar. We can see that it has, in fact, a larger dipole moment. The dipole moment is almost 5 times bigger than it is on HBr. So, what does this have to do with intermolecular forces? We saw that the dispersion forces were caused by instantaneous dipoles and the attractions between them. So you can imagine that if you had a permanent dipole moment, like these molecules do, there would also be a force of attraction between molecules. And in many cases, it would actually be stronger than the dispersion forces. So what we see when we have polar molecules is that we still have dispersion forces, but now we have another intermolecular force at play. We call it a dipole-dipole interaction. And these intermolecular forces will be operative anytime we have two polar molecules next to one another. If you look at acetonitrile and think about how it might arrange itself in the solid state, that's shown here on the left. Okay, you might think that it would just be kind of a head-to-tail kind of packing between the negative nitrogen end of the molecule and the positive CH3 end of the molecule. But remember that the molecules have to pack themselves into a three-dimensional shape to make a crystal. And so because of that, we actually get this herringbone pattern. But you can see that each negative nitrogen actually has, at least in this two-dimensional projection, at least 3 positively charged CH3 groups that are in close proximity to it. And so those are the dipole-dipole interactions that make acetonitrile a solid to a relatively high temperature for such a small molecule. Let's take a look at a series of molecules that are all about the same size but have different dipole moments, different levels of polarity, and let's think about the intermolecular forces in these substances. So if we start with propane, molecular weight of 44, carbon and hydrogen have slightly different electronegativities. However, they're not very different. And so you can see that the dipole moment here is tiny. And something you should remember is that chemists will generally consider the carbon-hydrogen bond to be nonpolar. So in hydrocarbons like propane, we really don't have polar molecules. The only thing that's really going on that's holding the propane molecules together is dispersion forces. And we see here that the boiling point is 231 Kelvin. And that's consistent with the fact that you know propane is a gas at room temperature. If we go to dimethyl ether, which is almost the same molecular weight, we get now non-negligible dipole moment. And the boiling point, it goes up a little bit. It goes up by 17 Kelvin. So we're adding in a bit of a dipole moment on top of the dispersion forces that are already there. Then when we go to acetaldehyde, which shape is shown here, the dipole moment basically doubles, and the boiling point now is quite close to room temperature. If we were to go to acetonitrile, which we were talking about on the last couple of slides, the dipole moment goes up again, almost tripling from the value it was in dimethyl ether, and we can see now the boiling point is going up to 355 Kelvin. So what we see is that in a series of molecules that all have very similar dispersion forces, as the dipole moment goes up, as the molecule becomes more polar, the intermolecular forces are stronger and we get higher boiling points. Okay, let's now turn our attention to the hydrogen halides. Okay, these are diatomic molecules between hydrogen and one of the halogens. What I show here are the molar masses and the dipole moments of these four molecules. We discussed the dipole moments actually back in chapter 8 of these same molecules. What I want you to do is pause the video and make predictions that as you go down from HF to HI, what's going to happen to the strength of the dispersion forces? And what's going to happen to the strength of the dipole-dipole interactions? And when we combine these two, what kind of predictions would you make for the overall strength of the intermolecular forces, which is going to be manifest in the boiling point? Higher boiling point would be stronger intermolecular forces, and a lower boiling point, the opposite. Pause the video, make those predictions, think about it a little bit. It's not that easy of a question. Then come back and we're going to discuss it. Okay, what did you predict? Let's go through it together and see if your thinking matches mine. So if we think about the dispersion forces, right, we know that those go up as the mass of the molecule goes up. And as you go from HF to HCl to HBr to HI, the molecules are getting heavier. The halogen has more electrons. The dispersion forces are going to get stronger. On the other hand, when we think about the dipole-dipole interactions, HF is the most polar molecule. It has the largest dipole moment, and HI has really a pretty puny or small dipole moment. So we expect the opposite trend. As we go from HF to HI, the dipole-dipole interactions are going to get weaker. And so then we're left with a bit of a conundrum here in predicting the overall strength of the intermolecular forces. It depends on whether we think the dispersion forces are stronger or the dipole-dipole forces are stronger. Let's just reveal the boiling points and see what the answer is. All right, we're going to start at the bottom with HI. Okay, it's got a boiling point of 238 Kelvin. HI is a gas at room temperature. And so that's, okay, stronger than something like oxygen or nitrogen, but not all that strong. If we look at HBr, it actually has a lower boiling point. So that's telling us that the intermolecular forces are weaker in HBr. And if we look at HCl, they get weaker still. Okay, so the trend up to this point is predicting that the dispersion forces are going to be more important than the dipole-dipole interactions, right? Because going down, we're seeing the boiling point go up, which is what would have been predicted from dispersion forces. So then let's make a guess for HF. I don't know. Looks like maybe If the trend continues, it might be 150 or 160 Kelvin boiling point. What is the boiling point of HF? Oh, 293. It's way higher than all the others. I didn't see that coming. Well, actually, I did see that coming because I created this lecture, but you might not have seen it coming. What's going on here? What is responsible for this anomalously high boiling point in HF? It's telling us that the intermolecular forces in HF are much stronger than we would have expected. Now, graphically, we can plot this data, and that's what's shown with the green curve here. All right, so here's the boiling point of HI, HBr, HCl, kind of going down slowly, and then boom, jumps up a bunch when we get to HF. If we look at the other molecules that are formed between hydrogen and the other p-block elements, we see largely a similar trend. If we were to look at group 6A, we see H2TE, hydrogen telluride, has a boiling point that's 260 Kelvin. It goes down when we go to H2 selenium, and down again a bit more when we go to H2S, hydrogen sulfide, and then jumps up a lot when we get to water. If we were to look at the group 5A hydrides, we see the same sort of trend, trending downward because the dispersion forces are getting smaller, but then unexpectedly, you might say, jumps up when we get to ammonia. Now, for the group 4 hydrides, we don't see this trend. Methane actually has a really low boiling point. Of course, these molecules, the shape of them being tetrahedral with no non-bonding electron pairs, we would get nonpolar molecules. And then we also have the fact that the difference in electronegativity there is very small. So those molecules are largely nonpolar, and really the only thing going on there is dispersion forces. But we can clearly see that something special is happening when we have hydrogen that's bonded to either the nitrogen, the fluorine, or the oxygen. Okay, and what that special thing is a particularly strong kind of dipole-dipole interaction that we call a hydrogen bond. And we're going to expect to see hydrogen bonding when we have molecules where we have hydrogen bonded to either fluorine, oxygen, or nitrogen. And on a neighboring molecule, we have a non-bonding electron pair on one of those electronegative atoms. And so we can think about the dipole moment of that kind of a bond, and that's shown here. But that kind of doesn't really give us the full picture of why this is such a strong dipole-dipole interaction. The reason why is because, remember, hydrogen doesn't have any core electrons. So in an HF molecule, the only electrons that are counted as being part of the hydrogen are those that are shared in the bond with fluorine. And fluorine is the most electronegative element. So it is pulling those electrons towards itself. And in the process, it basically leaves something that looks like a bare proton, a bare positively charged nucleus with no electrons to shield it. And that nearly bare proton can actually then interact really strongly with non-bonding electron pairs on a neighboring electronegative atom. So if we were to draw that interaction, it would look like this. Here's our hydrogen bond, which we show in the dotted lines between the hydrogen on one water molecule and the oxygen on a neighboring water molecule. Here's a similar interaction in HF and also in ammonia. Okay, I do want to stress right now that this interaction, which we call a hydrogen bond, is an electrostatic interaction that is really like a strong dipole-dipole interaction. It's not a true covalent bond because the Pauli exclusion principle is telling us that hydrogen can't make two bonds anyway. So it makes a covalent bond to the oxygen in the molecule in which it belongs. And then at this quite strong electrostatic interaction, the hydrogen bond to a neighboring molecule. Now we can get also hydrogen bonds between different kinds of molecules, like between a water and an ammonia, as shown here. So in mixtures of substances with the right kinds of structures, we can also get hydrogen bonding. Okay, let's stop now and do a problem. Here I've given you three different molecules: acetic acid, propanol and acetone. What I want you to do is to tell me, in these substances, do we expect to have dipole-dipole interactions? A. And B, do we expect to have hydrogen bonding? So as a little clue as how to answer this question, you have to first draw the Lewis structure to figure out how the atoms are connected. Then you have to think about whether the molecule is polar or not. And if it is polar, then you're going to have dipole-dipole interactions. And if you've got the conditions I just talked about on the last two slides, we could get hydrogen bonding. I'd like you to pause the video, draw the Lewis structures, make these predictions, then come back and we'll go over the answers. Okay, well, let's talk about the molecules. We need to start by drawing the Lewis structure. That's always the first step in answering this kind of question. So the Lewis structure for acetic acid looks like this. Now you might be thinking, hey, Dr. Woodward, it wasn't that easy to figure out how all these atoms are connected just from this formula. How do I know this is the structure? That's a fair point, but here's some things that can help you to draw Lewis structures like this. So first of all, in organic molecules, more often than not, when we have neutral molecules, the formal charges are all going to be 0. And to get that, it means that each carbon is going to make 4 bonds, each oxygen is going to make 2 bonds, and each hydrogen is going to make 1 bond. And if you end up with a molecule where you've got a non-bonding electron pair on a carbon, right, that's probably not the right molecule for something we're going to see in this class. So that can kind of help you. The other thing you might want to remember is all of the organic acids, a big group of compounds which are called carboxylic acids, have this C double bond O OH group. Okay, that's what makes them acids. If we look at propanol, in some ways it's a little bit easier. This is the structure of propanol. It's like an alkane with carbon-carbon and carbon-hydrogen bonds, but we've replaced one of the hydrogens with an OH group. Or if you want to think about it, we put an oxygen in between one of the carbon-hydrogen bonds. And then for acetone, the last molecule here, its Lewis structure looks like this. We have a molecule that at this central carbon forms a double bond to this oxygen and single bonds to each of the CH3 groups. It has a trigonoplanar geometry here. This is the simplest example of a class of organic compounds called ketones. Okay, so now having done the Lewis structures here, we can make some predictions about the intermolecular forces. You should be able to see that because the carbon-oxygen bond is going to be polar, oxygen is much more electronegative than carbon, you're going to have bond dipoles, and the geometries of these molecules are such that the bond dipoles are not going to cancel. So all 3 molecules are polar. And that means that all 3 molecules will experience dipole-dipole interactions. Now the next question is, what about the hydrogen bonding? And for that, we need 2 things. We need hydrogen bonded to either oxygen, nitrogen, or fluorine, and we have that in acetic acid. And then somewhere in the molecule, we need a non-bonding electron pair on one of those electronegative atoms, and of course you see that we have that. So acetic acid can definitely hydrogen bond to other acetic acid molecules. In propanol, we also have an OH bond, and so we can also get hydrogen bonding in propanol. But in acetone, although the molecule has both oxygen and hydrogen, there is no OH bond. And so that means we will not see hydrogen bonding in acetone. Dipole-dipole, yes, but hydrogen bonding, no. We could look at images of these molecules that show the kind of hydrogen bonding we get in the first 2. So in acetic acid, you can see the structure is such that one pair of acetic acid molecules can actually form 2 hydrogen bonds to each other. Whereas in propanol, they can only form 1 hydrogen bond. And because of that, the intermolecular forces in acetic acid are stronger than in 1-propanol, even though they both have the same molecular weight. So dispersion forces to a first approximation are equal, but the hydrogen bonding is stronger in acetic acid. Consequently, the boiling point is about 20 Kelvin higher in acetic acid than it is in propanol. Acetone, which is shown here, and doesn't hydrogen bond, although it has a very similar molar mass. It has the same kind of dispersion forces we have in the other two substances, but the lack of hydrogen bonding means that overall the intermolecular forces are weaker, and because of that, it has a boiling point that is, I would say, substantially lower. Okay, let's come back to some of the many important implications of hydrogen bonding. So one of them has to do with water itself. I mean, life on Earth depends on the properties of water. But water is only a liquid, as we saw in some of the slides earlier, because of hydrogen bonding. When you have water that is cooled below its freezing point and forms a crystalline solid, which we call ice, you get this kind of arrangement. This is a two-dimensional projection, but each water molecule, the hydrogen atoms on it are forming hydrogen bonds to neighboring water molecules, and the non-bonding electron pairs are also hydrogen bonding to different water molecules. We can only see one of those two here. But the bottom line is that each water molecule forms 4 hydrogen bonds to its neighbors. And the pattern that allows it to form these connections is actually this kind of hexagonal pattern that we see here. And so one of the implications of that is that we oftentimes will see hexagonal crystals of water. Here we see the hexagonal pattern reflected in this snowflake. To get the right pattern, we actually leave a little bit of empty space in between these hexagons. That means that the water molecules are not packed together as closely as we might expect based just on their shape. Okay, and that means that the density of ice is a little lower than we might expect. And when water melts and the molecules start tumbling around and moving and jostling each other, the structure basically kind of collapses. And because of that, the density goes up. So water is rather unusual in that the solid has a lower density than the liquid. That's important for a lot of things. I mean, imagine what nature would be like if the opposite were true. It means that lakes and rivers would freeze from the bottom up, or even if they froze at the top, the ice would sink to the bottom. That will have major implications for aquatic life on our planet. And in fact, the density decrease is not that small. The density goes down by about 9% on freezing. And this is unusual. Most substances, here's tetrachloromethane, actually become more dense when they go into the solid state. Another implication of hydrogen bonding we can see in the double helix structure of DNA. These blue ribbons represent the sugar phosphate backbone of a strand of DNA. And off of these sugar phosphate backbone, we have these what are called base pairs. And the base pairs, there are 4 different types: thymine, adenine, cytosine, and guanine. And here we're seeing the actual atomic structure of the base pair. And what you can see is that the thymine and the adenine are complementary in such a way that we can form 2 hydrogen bonds between these base pairs. Whereas the cytosine and the guanine can actually form 3 hydrogen bonds with the other base that makes a pair. Because of that, the double-stranded DNA is such that everywhere we have a T or a thymine, on the opposite side, on the other strand, we have an adenine. And everywhere we have a guanine, on the opposite strand, we have a cytosine. Okay, and so this is what holds the double helix together. But because it's a hydrogen bond, it's strong enough to hold the double helix together, but not so strong that it can't come apart. And so when you have cell division, actually the DNA double helix will unravel, and then you get replication. So another strand comes along, and it is constructed in such a way that it matches the first strand. We have to have the same sequence of G, A, T, C, so forth and so on. Okay, and that's how genetic information is encoded. You can see that hydrogen bonding plays a pivotal role in life. The last kind of intermolecular force I want to talk about is called an ion-dipole interaction. Right, so we saw that dipole-dipole interactions, the positive end of one molecule with the negative end of another, are reasonably strong. And then we saw hydrogen bonding could be even stronger, and it's a kind of super dipole-dipole interaction. What about if we had a dipole and then a true ion? like sodium or chlorine. Okay, then we get something which we call an ion-dipole interaction. And you can see here this sodium ion, if it were in water, it would be surrounded by the negative oxygen side of the water molecule. And the ion-dipole interactions are the strongest of the intermolecular forces. And in fact, they have to be pretty strong because if you think about sodium chloride, go back to chapter 8, we found that the ionic bonding is very strong. The melting point, the boiling point are very high. It's hundreds and hundreds of kilojoules, right, is the lattice energy. How is it then that when you put it in water, it just falls apart? And the reason why that can happen is because although we are breaking ionic bonds, we're making a whole bunch of ion-dipole interactions, and they are enough to compensate for the lost ionic bonding. So this kind of intermolecular force we're going to see when we put ions into polar liquids. Here's a little flow chart that you might use for identifying what kind of intermolecular forces are operative in any substance or mixture. You can kind of follow this. If you want to get ionic bonding, which is a chemical bond really, then you need cations and anions. If you want to get ion-dipole interactions, you need ions plus polar molecules. If you want to get hydrogen bonding, we're going to need these special kind of molecules where the hydrogen is bonded to either fluorine, oxygen, or nitrogen. If you want to get dipole-dipole forces, you just need a polar molecule. And then absent all of those things, dispersion forces will be the only things that are operative. But don't be misled in thinking that you can only have one kind of intermolecular force. Many types of intermolecular forces might all be operative at once. So one of the things to remember is always, in any substance, in any mixture, we're going to have dispersion forces. When we have hydrogen bonding, that's always going to be taking place in molecules that are also polar. So dipole-dipole interactions and hydrogen bonding go together. And then also we can look at the kind of energies of these interactions. To put this energy scale in context, keep in mind if we go back to chapter 8, we saw that covalent bonds typically have bond enthalpies that are hundreds of kilojoules per mole. 200, 300, up to something like nitrogen might be 800 or 900 with a triple bond. And so we can see here that the strength of the intermolecular forces are in fact quite a bit smaller. Also notice that dispersion forces, which we might think of as the weakest, and they can be weak in substances like helium, very light substances. But also notice that, the dispersion forces can get pretty strong. They can definitely be stronger than the dipole-dipole interactions and comparable to the hydrogen bonding. But it just depends on the details of how many electrons there are in a molecule, how heavy the molecule is. Okay, let's finish this lecture with one more problem to see if you can put all of this together. Here I've given you 3 different substances: sulfur dioxide, boron trifluoride, and sulfur trioxide. What I want you to do is, first of all, calculate the molar mass of each, and then I want you to draw the Lewis structure. And then why don't we do a little bit of review from chapter 10, getting ready for the final exam. I want you to predict the shape of the molecule. And then from that, I want you to tell me if the molecule is polar or nonpolar. And finally, then, we can make a prediction about the kinds of intermolecular forces that are present. Pause the video, work through that, make all your predictions, and then come back and we'll go over the answers. Okay, how did you do? Well, let's go through the answers and see. All right, well, we can determine the molecular weights pretty readily. We just have to add up the weights of the atoms that make up the molecule. And from that, we see that SO2 and BF3 are almost the same, and sulfur trioxide is a bit heavier. Now let's do the Lewis structures. Here's the Lewis structure for SO2. This would have a resonance, and I'm only drawing one of 2 resonance structures, but the fact that it has a resonance isn't really that important for making the predictions that we have to do right here. The Lewis structure for BF3 looks like this. You might recall, or hopefully you can recall, that this is an exception to the octet rule. We might be tempted to put a double bond in this molecule, but because the fluorine is so electronegative and the boron so electropositive, the fluorine just doesn't really want to share its electrons enough to make a double bond. So we get this Lewis structure. And then SO3 looks similar, but here sulfur and oxygen actually are neighbors, and so they're not that different in electronegativity. And we do get a double bond in this molecule. There are 3 resonance forms of that, but just like SO2, that's not so important for answering this question. Given this, we can predict the shapes of the molecules. SO2 has a trigonal planar electron domain geometry, and so therefore, because one of those electron domains is a non-bonding pair, its shape would be bent. BF3 and SO3 both have 3 electron domains and no non-bonding pairs, so their electron domain geometry and molecular geometries are both trigonal planar. From this, now we can make predictions about the polarities of the molecules. The bent molecule here, SO2, is going to be polar. The dipoles are not going to cancel out. It turns out that the dipole moment on an SO2 molecule is about 1.6 dBi. That's not something you would be expected to be able to predict or calculate. BF3, being trigonal planar, is nonpolar, as is SO3. So we have one polar molecule and 2 nonpolar molecules. And now we're in a position to predict what intermolecular forces are at work. So they all have dispersion forces, and SO2 is also going to have, on top of that, dipole-dipole interactions because it's a polar molecule. The other 2, being nonpolar, will not. And of course, we won't have hydrogen bonding because, well, there's no hydrogen in these molecules. And we're not going to have ion-dipole forces because, well, there's no ions around. So that's the answer. But now let's just finish by making some kind of predictions about the relative boiling points of these 3 molecules. So what do you think? Which one would have the lowest boiling point? Which one would have the highest boiling point? See if you can rank order them. The natural logic that one would use is to say that boron trifluoride is going to have the weakest intermolecular forces. I mean, it only has dispersion forces, and it is lighter than SO3, so therefore we expect its dispersion forces to be less than SO3. And then when comparing SO2 to the other 2 molecules, it's a little bit ambiguous. We definitely would predict that SO2 should be stronger intermolecular forces and higher boiling point than BF3, because the dispersion forces should be comparable since the molecular weights are similar, and this one is polar and this one nonpolar. But then when comparing SO2 to SO3, we're in that gray area again. I probably would kind of guess that the molecular weights aren't that different, so probably SO2 is going to be a little bit higher boiling point than SO3. Well, let's reveal the boiling points and see what nature is telling us. So the boiling point of SO2 is 263 Kelvin. It's a gas at room temperature. If we look at BF3, its boiling point is 90 degrees lower. Right? So we see, as expected, the intermolecular forces are stronger in SO2 than they are in BF3. When we come to SO3, my prediction was it would be somewhere in between these 2. But we see actually the boiling point is higher than either of them. Okay, so how do we understand that? I mean, really, there's only one way to understand that, and that is to say that the dispersion forces in SO3 must be strong enough that even though we have dipole-dipole interactions in SO2, the dispersion forces are the dominant factor that make the boiling point of SO3 higher than SO2. Sometimes it's a little bit ambiguous what we can make in terms of predictions of boiling points, but as long as we have molecular weights that are pretty similar, then we can use this idea that adding in dipole-dipole pushes the boiling point up. Adding in hydrogen bonding would push it up further. All right, well, I hope you've enjoyed this section. It is the key or the heart to this whole chapter, and in the sections that follow, we're going to talk about different properties of liquids and how they depend on the intermolecular forces.